Hi, everybody. Thanks for joining us for, what is astonishingly, I think, our 21st Occ-COVID event, trying to understand SARS-CoV-2 and its impact in workplaces, and most especially how we can prevent transmission and prevent illness in workers' workplaces, and of course the community that they all go home to. So I'm really excited today about the panel that we've put together, trying to figure out ways how to make 2022 truly happy, healthy, and new, because we need some new ideas, I think we all agree. And I'm really excited to have our speakers with us, Dr. Ashley Tweet, Dr. Dalia Hassan, Matt Oliver, Dr. Raymond Tellier, and Renee LeBlanc. We are going to shift our order in order to accommodate. Raymond's going to go first, as we all are very interested in what's going on with Omicron, and I guess any information on beyond that in terms of variants of concern and what that means in the short term and the long term. So I will turn it actually over to Kevin, who's going to do the bios and speaker introductions. Thanks.
Okay, hello everyone. My name is Kevin Hedges. I'm an occupational hygienist with OCAM, and it gives me great pleasure to introduce our speakers today. And we are really grateful to our speakers who are, under a lot of demand at the moment, and this is a pretty crazy time that we have. So as a result, Dr. Tellier has moved forward just to save him some more time. So Dr. Tellier is an associate professor at the Department of Microbiology and Immunology, the Department of Medicine at McGill. He has a tremendous range of experience in coronavirus, influenza, flu, hepatitis, medical and molecular microbiology. So he's a medical doctor, and he's also a medical doctor microbiologist. And he also, I believe he's actually got under his belt, and there might be more now, 112 peer-reviewed scientific articles. So Dr. Tellier actually was brought into the mix, I think it was July 2020, through Alex Farquhar, who's done a fabulous job, brought Raymond into the mix to work with us. So Raymond's actually introduced Lindsay Marr, John Conley, and Don Milton at a previous webinar, and he's also presented himself on the Err on the Side of Caution. So it really is fabulous to have Dr. Tellier back again, especially now we all want to hear what's happening with Omicron. So I'll hand you over to Dr. Tellier. Thanks, Dr. Tellier.
Very kind introduction. So I just thought that we would take this opportunity today to review a little bit the variant of concern that we have suffered from, including some information about the Omicron. And I say some because the picture is moving very, very rapidly. And already since I finished my slide yesterday, there are some new information that are coming all the time. So, of course, we're talking about the SARS coronavirus 2, which is the causal agent of COVID. And this is a cartoon representation of coronaviruses. They all look the same. These are viruses that are enveloped. So you have the genome of the virus that is complex with a nucleocapsid protein surrounded by a membrane acquired from the cell from which they bud off. And in this membrane, you have embedded a transmembrane glycoprotein, which is the spike glycoprotein, a very important protein in the life cycle of the virus. It is responsible for attachment of the virus to its target cells and mediating the entry of the virus in the cell. It is also the antigen that is used in almost all of the vaccines that are used worldwide, including the 2 mRNA vaccines and the adenovirus vector-based vaccine, the AstraZeneca and the Johnson & Johnson. Coronavirus have a RNA genome, and as far as RNA viruses are concerned, they have the largest RNA genome. So the thing is that viruses mutate, that's what they do, but different viruses will mutate at different rate, and RNA viruses will mutate more than DNA viruses, and shorter genome viruses will mutate more rapidly than larger genome viruses, and some viruses mutate at the highest rate that they can without losing their information content, so it's part of their strategy to adapt to a changing environment. And in fact, coronavirus in general and SARS coronavirus too are not the fastest mutating viruses. The COVID coronavirus has only half the rate of mutation of influenza A and 25% of the rate of mutation of HIV. So it's not a record breaker, but nonetheless it mutates. And we always knew when this pandemic started that if the pandemic was allowed to last for a long time, there would be mutation that would accumulate in some viruses. And at some point, some of them would have accumulated enough mutations away from the original strain that they would become distinct lineage. And one of the first striking example of that was the emergence of what was known at the time as the British variant, and it became known as the Alpha variant. And if you can look here at this phylogenetic tree, you can see that there was an isolate which came from South England, which was noticeably standing apart from the rest of the other viruses that were circulating at the time in the United Kingdom. And some of the mutations were occurring in the spike protein at really key areas. So you have here a representation in red is the spike glycoprotein that is on the membrane of the virus, and it's binding to the ACE2 glycoprotein, which is a cellular protein that's the receptor that the virus uses. And you can see that one of the defining mutations of the Alpha variant, this British variant became to be known. It's a mutation that improved the binding of the spike glycoprotein to its receptor. And there's also a mutation at another site here, which is known as the furin cleavage site, which is a very, very important site for the capacity of the virus to mutate in the upper respiratory tract, which is one of the reasons why this virus is so much more contagious than the original SARS virus, is that it can cause an infection in the upper respiratory tract, and some mutation at this site will improve that capacity. And this deletion here probably allow it to escape a little bit the immune response that had been generated by vaccine at the time. And the suspicion that this virus, this variant, could be much more infectious was soon confirmed when you saw that even though there was a very high background of COVID activity in the UK with the standard lineage, but nonetheless, the Alpha variant was able to come in, outcompete the other COVID coronavirus that were there, and became very rapidly the dominant SARS coronavirus 2 strain in the UK, and actually spread worldwide, including in North America, in Canada, and in the United States. I'm showing you here a paper that was published in February, in which they were predicting that it would become dominant in the United States, which indeed came to pass, and it became dominant as well in Quebec. There was another point of contention at the time as to whether or not this Alpha variant would also be associated with a greater severity of disease. And as it turned out, it was associated with a greater severity of disease. So there you have it, in the middle of the pandemic, the evolution of a variant that is both more contagious and associated with a greater severity of disease. Okay. So another similar story soon happened in South Africa with a variant that was initially known as the B.1.351 that became known as the Beta variant. And it's a very similar story. It's a strain of coronavirus that was markedly different from the original strain, with some key mutations that were worrisome as to the phenotype of the virus. It quickly became dominant in South Africa and spread throughout the world. And you have a similar story with the Gamma variant, which was initially known as the Brazilian variant, and which first was detected in Brazil, and soon enough started to spread around the world. However, neither the Beta nor the Gamma variant were able to displace the Alpha variant. The Alpha was the most fit variant at the time, and the Alpha remained dominant. Now, at the time, there were several studies that were done to try to see if these variants, the Alpha, the Beta, and the Gamma, were still being covered by the vaccines that we had. And there are several different ways to go about this, one of which is to measure in the laboratory the neutralizing antibody titer using sera from people that have been vaccinated. And what you do is that you dilute the sera to serial dilution, and you can see which dilution still can neutralize the virus in an infectivity assay, and that's your titer. And what you see is that if you introduce different mutation that you found in this variant, you do see a noticeable drop in the neutralizing antibody titer. So there is some degree of immune escape from the immunity that is conferred by the vaccine. However, these are dilutions of plasma, and of course your own plasma, your own serum is not diluted, and as long as you remain with the titer of neutralizing antibody that it's high enough, you would expect that the vaccine would continue to be effective. Not only that, but we also know that the vaccines are triggering other aspects of the immune response that are not measured by neutralizing antibodies, such as antibody that trigger the complement or antibody involved in the antibody-dependent cytotoxic killing, or also the cellular mediated immunity with T cells. So with all of this, it was expected that in the field, people that have been vaccinated with the current vaccine would be protected against this variant, and indeed this has been borne out, is that the current vaccine were very effective to protect against infection with the Alpha, Beta, and Gamma variant, and also to protect, even if you had a breakthrough infection, you had a very, very strong protection against severe disease and hospitalization. But as the saying goes, there's always a bigger fish. And the next variant of concern that emerged, that was detected initially in India, was the Delta variant, which accumulated also more mutation in the spike glycoprotein, including a defining mutation in the furin cleavage site. This was the a mutation with the arginine amino acid this time, and it makes the furin cleavage site so much more effective that this virus was now able to replicate faster and so build up an infectious titer much more rapidly. And it was expected, based largely on that, that this is a variant that would be very, very contagious. And what you saw, and this is an illustration of one of the ways in which you can quantify the contagiosity of an infectious agent. It is the basic reproduction parameter, or R0, which is defined as the average number of patients that a sick person will infect in a completely immune population at a time where you are not putting any barrier to its propagation. So the R0 value is very much a property of the virus or of the microbe under consideration. It should not be confused with the effective reproduction parameter, which is what you measure in the field at a time where you have a fraction of the population that is immune, where you have people wearing masks, ventilating their room, etc. But if you have R0 of 6, which is roughly the measured value for the Delta variant, the R0 for the Delta variant is estimated between 6 and 7, compared to 2.7 for the original strain of coronavirus, of the COVID coronavirus, you can see that with R0 of 6, an outbreak will take off and become very, very large, much, much more rapidly. And this is because the virus was replicating a lot faster. And indeed, we saw that this variant was extremely effective at transmission. In the UK, it quickly became the dominant strain. And we saw also in Quebec exactly the same thing. You can see that we had the Alpha variant that was dominant, and then the Delta variant was introduced somehow. And even though there was a high background of COVID activity with the Alpha variant, the Delta variant was able to outcompete the Alpha variant and has become the dominant strain. A few months ago, it became, in fact, virtually 100% of the infection in Quebec were caused by the Delta variant. Interestingly enough, if you plot the genetic distance of the different variant compared to the original Wuhan strain, you can see that the variant that was the most distant was the Beta variant, which was not the most fit. So the genetic distance between the original strain and the variant is not the sole predictor of how fit a new variant is going to be. Now, true to our principles that there's always a bigger fish, we are now monitoring the emergence of yet another variant of concern, which is the Omicron variant. You can see on that slide, by the way, that there were other variants which were variant of interest, but never got promoted to variant of concern because they went essentially nowhere. And not all of them are there. I remember there was a Japanese paper about the Lambda variant where they studied its immune escape property from the vaccine in vitro, and were making apocalyptic prediction about the behavior of Lambda. But Lambda essentially fizzled. It could not outcompete the Delta variant. So it's very difficult to make prediction in this game. But the Omicron variant was initially described in South Africa, and it was striking because it had more than 50 mutations acquired from the original strain, 36 of which were in the spike glycoprotein. And then you can see of these 36, 26 are unique, have never been seen before. Others have been seen before, and we think some of their properties. And right off the bat, there was the grave concern about this variant as to whether it would be able to become an immune escape mutant. What we are seeing with this variant is that it's even more transmissible than the Delta variant. And you can see that in South Africa, the Omicron variant, this slide is already outdated. There's another one that I've seen today where it has become now the dominant and indeed almost the only strain present in South Africa. And we're seeing the same thing worldwide. You can see that the Omicron variant is being transmitted at a pace that is much more steep than what we saw with the other variant. And I can show you data in my own laboratory where we began to do some screening for the Omicron variant. And we started with a background of 100% Delta. And you can see that in the week of December 2, essentially 0% of our sample were Omicron. It was 100% Delta. And then we started to see a few, and last Sunday I was at 1%, and the day after that I was at 19%, and yesterday we were at 49% of the sample that we tested in laboratory that are now Omicron. So it's very, very fast. And at that rate, I think that we will be soon in the same position in Ontario, probably by the end of next week, where 100% of our cases of COVID are going to be caused by the Omicron variant. So the Delta, which we thought was very transmissible and very fit, is being eaten away by the Omicron variant. The same kind of laboratory study have been done with the serum of people that were vaccinated. The good news is that the vaccines are not completely ineffective. People were expecting to see no protection at all. The bad news is that this is the variant that has the biggest escape from immunity confirmed by the vaccine yet. So you can see here that you have essentially a 40-fold drop in neutralizing antibody titer. Now, the thing is that if you start with a very high titer as measured against the original strain, a 40-fold drop means that in your own undiluted plasma, you might have enough neutralizing antibody to confer protection. However, it might be a very good idea to boost your titer by a booster with vaccination, and these initial studies suggested that the vaccine may very well be effective, but they might need a booster. Now, as I have hinted previously, these type of laboratory studies do not tell the whole picture. You also want to see what is happening in the field, and we're beginning to see some data that's emerging. So this is a study from South Africa that everybody is quoting, where essentially if you have had 2 doses of a vaccine, mRNA vaccine, the protection against infection is significantly lower, about 30% or so. The protection against severe disease requiring hospitalization remains quite good at 70%, but it's significantly lower than the 93% that you would see against the alpha, beta, gamma, delta variant. So a significant drop in protection, although you still retain some efficacy. And what we're seeing now trickling in are some studies that shows, however, that if you have a 3rd dose as a booster, you bring it back to a level of performance that is quite close to what you see against the other variant, to the point that Dr. Fauci was declaring the other day that they do not see the need right now to prepare an updated version of the mRNA vaccine. They think that a booster, a 3rd dose with the current formulation would be good enough, but it's really imperative that we avail ourselves of the protection with these vaccines. So this is what I had prepared for you today, and I'd be happy to listen to your comment and question. Thank you very much.
Thank you very much, Dr. Tellier. I see that Dorothy Wigmore's put a couple of questions in the chat box here, and I kind of was going to ask the same question as well. Anyone else can ask questions too if they want, either in the chat box or by raising their hand. And I know, last year we knew that airborne precautions were needed. China introduced airborne precautions and they were able to flatten the curve. So Dorothy's 2 questions. Firstly is, what makes the Omicron variant more transmissible? And the second question, does the variant behave differently in the air? I wonder if maybe you could just address those questions.
We don't have all the answers to this question. As to the first question, it's very difficult to predict or explain the behavior of a virus just based on its genetic sequence, but we do recognize some mutations that have an effect of transmissibility, including the 501Y mutation, which increased the affinity of the receptor of the spike glycoprotein to the receptor, including a mutation in the furin cleavage site and some other mutation that plays a role. There's a study that has just come out in Hong Kong where they claim to observe at the level of the bronchia a much faster replication rate of the Omicron variant as opposed to other strains. So that may be a clue, although other studies and other data are needed to understand this. As to the second question, does the variant behave differently in the air? It has not been studied yet. There is, as you know, immense amount of data by now to the effect that COVID is transmitted by aerosol in great part. Okay, there are different modes of transmission, and aerosol transmission is certainly one of them. There is a lot of data to do that. And very few studies have been done with variants as opposed to the original strain, but there are at least 2 studies that suggested that the alpha variant was better than the original strain in aerosol transmission. Measurement of aerosolized virus by a collection of aerosol from sick patients have shown that you have a larger amount of aerosolized virus with the alpha variant than with the original strain. And you have also in animal-to-animal transmission study, the alpha variant had a superior performance in aerosol transmission than the original strain. I have not seen yet this type of measurement done with the Delta variant, even less so with the Omicron variant. But basically, I think it's logic to think that if a variant is more transmissible, it would have an improved performance across all its mode of transmission, including therefore aerosol transmission. And I would totally expect that it would have a better performance in aerosol transmission than the original strain, certainly not lesser.
Thanks very much, Dr. Tellier. And we know that you're going to pull away and then hopefully come back, with our panel session, which would be really great. Just for everyone's benefit,